talking with sequences and series. You guys have dealt with sequences before in geometry, probably a little bit in Algebra 1, but we're going to dive into them a little bit more, a little deeper. So the first ones we're going to talk about are going to be sequences. So here we go. First thing, let's define them. So an arithmetic sequence is going to be a sequence of terms in which the difference between any two consecutive, that might be a word we're not really familiar with. Consecutive is back to back, right after one another. The term is constant. We'll talk about what this actually means as far as real life in just a minute. A geometric sequence is a sequence of terms in which the ratio between any two consecutive terms is constant also. Arithmetic means you are adding, and geometric means you are multiplying. We will always be adding, and we will always be multiplying. You'll see what I mean in just a little bit. And so, just to give you an example, 2, 4, 6, 8, okay? This is an example of an arithmetic sequence because each time I'm adding by 2, add by 2, add by 2. And my common difference is plus 2. Now what I meant by you're always adding is, let's say I gave you something like this. 196, 92, 88. Okay, what am I doing here? What am I doing here? What am I doing here? So what did I say we were always pretending though? Not pretending. What did I say we're always doing in arithmetic sequences? Adding. So how can you rewrite that as an addition problem? You're adding a -4. So what if someone asks you what is your common difference here? Your common difference is not 4. Your common difference is a -4. You are always adding in these guys. Does that make sense? Geometric is the same kind of thing that's going to happen. If you have 1, no, we do that. No, let's not. Let's do careful, because when you're first looking at this, you're going to go, oh, add 7, and then add 14, right? But actually, times 2, times 2, that's going to be our common ratio. Yes?
Maybe also.
All right. Now, here's another example. Let's say we had 48. How do I get from here to here? Divide by 2, right? How do I get from here to here? How do I get from here to here? Finally. Now, what did I say we always write these as? How can you rewrite division as multiplication? What is the same thing as dividing by 2, but with multiplication? Well, let's go back to, again, we've done this before, but let's go back to middle school. Your teacher put 5/3 divided by 1/2. Did you do that? You did not divide by fractions. What did you do? Multiply by the... Now, does it have to be only with this case that you can do that? So here's what I'm asking you. What if you had 10 divided by 2? Could you rewrite that as a multiplication? Yes. What would you do? Keep, change, flip. Yes? So how can I change this dividing by 2 to actually multiplication problem? Multiplying by 1/2. And so when you rewrite these and we use these formulas, you always want to use multiplication for geometric. You always want to use addition for arithmetic. You cannot use subtraction, especially in the formulas I'm going to give you later on, and you cannot use division in the formulas I'm going to give you later on. You must write them as multiplication problems. If you don't, you're going to be in a world of trouble. You might want to get this lesson down because we are going to use this for series. Series are going to have to do with sequences. So I first need to understand sequences. Just like everything, how 6-1, 6-2 is going to depend on most of your knowledge from 6-1. We are also kind of taking a break from factoring and stuff, but like I said, since this is a good break, it might be a good shot for you to review that, because that's what killed almost every one of you on that Chapter 5 test. Remember how I told you if I gave you the graph, almost every one of you would be able to give me the parts where it's greater than 0 or less than 0? That rang true. Almost everyone got that question correct. But yet when I didn't give you the graphs and you had to come up with them on your own, you had to factor. You had to find the roots. All of our old stuff, we weren't as successful, which was kind of sad to me. So it's a good chance for you to go over your factoring, because factoring is not going to go away. Chapter 7 and Chapter 8 especially, factoring is huge. So this is a good chance. We're not going to use it a lot here, so it's a good chance for you to review it so that you're ready for the next couple chapters. So the other thing we need to finish up on is this idea of finite and infinite. Something that is finite has an end, so this ends, and this goes on forever. Forward. Yeah. Third. Okay. All right. So Lisa and Ray give the next few terms in the sequence 1, 1, 1, and they called it a sequence. Some kids get this word confused with a pattern. Yes, sequences all have a pattern. You are adding by the same thing every time, so that is a pattern. But not all patterns are sequences, because in order for it to be a sequence, you have to be adding the same number every single time. For a pattern, as long as you can see the repetition happening, it can change as long as the change makes some kind of sense. So here's what I mean. What am I adding each time here? 0, 0, and then from here to here, what did they add? 1, 1, or I'm sorry, 0, 0, 1, 0, 0. What's my pattern going to be? 1 and then 0, 0. Is that a pattern? Yes. Is it a sequence? No, because I'm adding 0, add 0, add 1. Do you see how I changed what I was adding? Remember, every time it's got to be the same thing. What am I adding in Ray's? 0, 0, 0. Adding 0, 0, 0, 0, 0. Does his common difference ever change? No. So which one actually has created a sequence? Ray. Has Lisa created a pattern? Yes. Do I know what's going to come next? Yes. Is it a sequence? No, because it changed what she was adding. You have to stay consistent throughout the entire thing. Plus 2, plus 2, plus 2, plus 2, plus 2, plus 2, and keep on going. It can never change. If it changes, it's not a sequence. Does that make sense? All right. So analyze these guys. The number of tiles. You see that this is 3 blocks, right? It's a 3 by 3, which is 9 blocks, right? 9 cubes. And this is a 3 by 4, which is 12. So how much did they add here?
3.
Right? And we'll actually just... How much did they add to get to here? How much did they add to get to here? Now, that would be a which one? Arithmetic or geometric? Be arithmetic. That's my common difference. What am I adding every time? And does this sequence go on forever, or would it end? It will be infinite and keep on going forever. Does that make sense?
No, I was just asking myself, how would it end?
Oh, yeah, it can't. It's going to keep on going. Now, just for a second, because this will help us out later on. Do you see, we're going to get this later on in terms of, we're going to get formulas, but I'm going to try to shape your brain to where the formulas come from right here. Do you see, this is my starting cube, right? How many 3's did I add to my starting one to get to here?
1.
So I added 3 there, right? Do you see my starting cube is still right here? Right? I'll color it in red. How many 3's did I add to this one? With me? How many 3's did I add to this one? Does that make sense? You don't have to write that. Just kind of keep that in mind. Just kind of hold that. Now, watch if I do this a different way. We're going to come up with 2 formulas, and I'm going to remind you back to this. We're going to come up with 2 formulas, and I'm going to remind you back to this. Do you see this is my starting one? Yes? And I added what to it? Okay? Now, do you see this is my second term right here? We'll do this in blue. This is my second one. That's this whole thing right here. How much did I add to it? Yes? And this is my third term. And what did I add to it? You guys kind of see something that I'm doing? Okay. It hopefully will make our next part a lot more clear. Alright, so let's go through this quickly. Number of toothpicks. Okay. Hopefully you can see 2, 4, 6, 8, 10, 12. Right? And that's 12 right there. 14, 16, 18, 20, 22. So to here, I added 10 and got 22 total toothpicks. And this would be the same here. So I added, so that was 22, 24, right? So I added 2, 4, 6, 8 to this one. So it gets a total of 30. You guys follow me? Is this a sequence? No. Why not? Because I change what I add, or if I change what I multiply by, it's not a... Alright, now, we can still look at this and just determine, is this finite or is this infinite? Well, let's keep going up. If I went here, this would be my next row, this would be my next row, and finally I'd have that point at the end, right? And I wouldn't be able to continue this pattern anymore, would I? So we would actually give this, and I'm going to cross this out, because it doesn't make sense to say it's not a sequence and then call it a finite sequence. So I would just say that this pattern is finite, just to give you an example, but we just decided that it was not a what. So it doesn't make sense in my mind to call it a finite sequence if it's not. I guess arithmetic sequences are always adding. Geometrics are always multiplying, and I guess they're saying a sequence is just a pattern. Do you get the difference? An algebra or arithmetic is always adding. So it's a type of sequence. A geometric is a type of sequence. This is neither one of those two. It's just a regular sequence or something that has a pattern. Do you get what I'm saying there now? So, be careful on this when they try to trick you. What are you trying to see if there's a pattern between? The number of rows. How many rows does this have? How many rows does this have? Rows. This one? Is this a series? I'm sorry, a sequence. Yes. And I'm adding one each time. So that's my common difference, is a positive 1. And it is a infinite sequence. Does everybody see what I just talked about there? Number of cubes. Now it's the same type of problem, huh? But now we're talking about the number of cubes. How many cubes does this have? How many cubes does this have? By the way, do you see the bottom is a 2 by 2? So how many cubes are on the bottom? 4 plus 2 more is? This is a 3 by 3. So that means that there's 9. A 3 by 2, which is 6 or 15, plus 3 more is 18. Does everybody see that? Then we have a 4 by 4, which is 16, but I can kind of stop there. I can probably stop here. If it is a series or if it's a sequence, I want to make sure the fourth one does. But watch right here. How much am I adding? Did I add 5 to get to here? So I know it's not arithmetic. How much did I multiply by? How much do I multiply by? Is it the same thing? So it's not a geometric, so I know it's neither, and it is a, infinite. Is there a pattern to this?
Yeah.
Yes. Like I can predict what the next thing looks like, but it's not a arithmetic or a geometric sequence because it's not adding or multiplying by the same number every time. So for homework, go ahead and try E, and it is only talking about the whole triangles. So do you see how it says the black triangles? How many black triangles are here? Not 4. Someone in my first period asked, well, what about the large triangle? No, they're not including that because that's not a whole triangle. It's a good question. They're only talking about the whole ones. Does that make sense? Try F. G and H. I'm also going to give you some skills practice. So I will be putting up the skills practice on Portal tonight, and I will be putting up the numbers that you should do. It won't be too many. It'll probably be a couple of, like 3 of the arithmetic and 3 of the geometric, using the formulas just so we make sure. These shouldn't take very long, so it should probably be, maybe 15 minutes of work to finish this. But I want to make sure we understand these. So here we go. This is what I was talking about. These are the formulas. Matt, you kind of referred to that idea of the power, which we're going to get to. So explicit formulas versus recursive formulas. Do you know how I have this? Like when I first did one, I did 2, 4, 6, 8, 10, blah, blah, blah. Well, do you see how all these numbers are part of a pattern, correct? So how do I tell you I'm talking about the third number in the pattern, Joel? How do I say that's the one I'm talking about? Well, this is referred to as A1 because it's the first term in the sequence. Why do we use A right here? What kind of pattern are we talking about when they put A there? An arithmetic. When they use the G, they're talking about geometric.
Can't you change those?
It could be, it doesn't matter, but we just use it to keep it kind of to make sense. But no, it doesn't have to be this. It's just telling you that this is for an arithmetic sequence, and we're using A1 because it's the first term. What would I refer to this as? A2, A3, And if I wanted to refer to any term, I would call it a to the n. Because that means it's any term you want n to be. If you want the 100th term, then n would turn into a 100. Does that make sense? Explicit formula says if you want a to the 100th term, you take the first term and add the common difference times n minus 1. Does everybody see how it says a is the first term, d is the common difference, and n is the nth term of the sequence? So whatever one you're trying to find. Nth, 100th, 150th, whatever term you're, the variable one, the one you're trying to find is the nth term. So it's the one that can change because it depends on which one you're trying to find. Doesn't this formula make sense to what I showed you at the beginning of the blocks? How many times am I multiplying d? N minus 1. It's always, if I'm on the 100th term, how many times am I multiplying it by? If I'm on the 100th term, how many times am I going to multiply the d by that? By what? Not the 100, but 99. Why? Let's go back to our blocks for a second to understand the explicit formula. Do you remember when I had you write this down? I said, this is our A1, this is our A2, A3, A4, correct? This is my original, this is my original, this is my original, and this is my original. Or what we refer to as, everything I colored in green is A1. Does that make sense? So does everybody see I have A1 right there? I have A1 plus what? 3. How many 3's? What is 2 minus 1? N minus 1. How many 3's? A1, right? That's what this stands for. Plus, I have 1, 2, 3's. What is N minus 1? You guys get what I'm putting down here? How many 3's were in this one? Well, we have A1 plus 3, and we have 3 of those 3's. Because from my original, to get to here, I've added 3 one time. To get to here, I've added 3 2 times. To get to here, I've added 3 3 times. That is called the explicit formula. You guys get what I'm talking about? So the explicit formula is really nice because it can find any term. The explicit form, I can find any term in the sequence. So all you have to know for this is you have to know, think about the things you need to know. You need to know your starting point. You need to know your common difference. And you need to know what term you're trying to find. So if you have that, you're golden to be able to find. That makes sense? Now watch what the recursive formula does. If I gave you this pattern right here, how can I find the next term? So what would my answer be?
18.
What would my next term be?
21.
What would my next term be?
24.
That is called the recursive formula. The recursive formula says you use the term in front of it and just add the common difference. So how do I get to my next term? I use the term in front of it and I just add another 3 because that's my common difference. And so I realize that it's 27. What does the recursive formula require you to have, though? The term in front of it. Do you get what I'm saying? So here's the reason why the recursive formula isn't as, I don't think it is as awesome. Find, for this one right here, using the recursive formula, I want the 100th term. Why does that suck? Because you got to take this and do what? Add 3. Add 3. Add, and you have to keep going until you get to the 99th one, and then you can finally add your final 3, and now you got the 100. Do you want to keep doing this, adding 3 100 times? Which one's going to be faster? Now, what if I said to find, what if I asked you to find the 12th term? If I ask you to find the 12th term, is it going to be faster to do the explicit, or is it going to be faster to do the recursive? It's going to be faster to do the recursive because I've already given you the 11th. So all you have to do is add 3. So do you see how the recursive, when you use the recursive versus when you use the explicit, they are the same kind of thing for arithmetic and geometric. For geometric, the explicit will find any term in your pattern. All you have to have is, what do you think G of 1 stands for? The first one. What does R stand for? The common ratio, what you were multiplying by, and the whatever term you want to find. Alright, so for these guys, the arithmetic and the geometric sequence, explicit formula and recursive are going to be very similar. For explicit, it will find any term, anywhere, wherever you want, as long as you have the first term and you have the common difference and you know what term you're trying to find. For recursive, you must know the number in front of it in order to find the next one. So like I said here, if you were trying to find A at 100, you would have to know, someone would have to tell you what A99 is, and then you would just add the common difference to get to the next one. But if you don't know it, you'd have to keep adding until you found it. It would take forever. This one right here, same thing with geometric. You would have to take the term before it, and you just multiply the common ratio. So recursive, you have to know the one in front of it. Explicit, you can find anyone, anywhere, anytime. All right. So which formula would you want to use if you determine the 95th term? Of either of these sequences, you'd want to use which one? Explicit. All right, so right here. I'm going to add some stuff to this. Just a little bit to this to make sense. All right. Identify each sequence as arithmetic, geometric, or neither. If possible, determine the 50th term of each sequence. So what am I doing? How do I get from here to here? Add 4. How do I get from here to here? What I always try to do is I try to add first. If that doesn't work, then I go to multiplication. If that doesn't work, then it's neither. So I do a couple because I want to make sure. Add 4. Does it change? Does my pattern change? So what kind of sequence is this? It's arithmetic. Is it infinite or finite? It's infinite. This keeps on going. If I was going to find, now watch this. What if I said the 9th term? If I asked you to find the 9th term, would you use the explicit formula, or would you use the recursive formula to find the 9th term? If I was doing this one, I would use the recursive. Why? Because they gave me, this is a 1, 2, 3, 4, 5, 6, 7, 8. So if I want to find the 9th term, all I have to do is take 23 and add 4 to it, and I realize 27 is my 9th term. And it's really fast and really easy for me to use recursive because it's not that far away. And it's faster. If they ask me for the 50th term, would I want to use the recursive? No, I'd want to use the explicit formula because I've got to, that's way too many terms that I have to add to get. In fact, I have to know my 49th term in order to be able to find my 50th. You guys with me? But explicit, all I have to do is A1 plus the common difference, and I'm going to have that how many times? 49 times. Because it's n minus 1. And n was 50. Does everybody understand how I got that 49? What was A1? A1 is negative 5. Negative 5 plus the common difference is, what am I adding each time? 4 times 49. And if I was doing this, I would actually do this in my head. 4 times 50 is what? 200. But I didn't have 4 times 50, did I? So 4 times 50 is 200. Well, that means that 4 times 49 is going to be just 4 less than that, so 196. Does everybody see how I got this to be 196 using my mental math? And then I subtract 5, because really, when I add a negative 5, those two cancel out, and I get 191 for my 50th term. How we doing? Last one that we're going to go over, and then, like I said, I'm going to give you some of these to try. So you have some in this book that you have to do, and then you're going to have to go on the portal, and I'm going to give you a skills practice, and I'm going to give you some page numbers, and only a couple problems to try, but they're going to be more similar to these types. All right? Here's a great question, and that's why we're going to end on this one. How do I get from here to here? What do I do?
Divide.
Divide by 3. How do I get from here to here? Divide by 3. From here to here, divide by 3. But the problem is, I told you at the beginning of this lesson, we're not allowed to write them using division, are we? What do I need my common ratio to be written as?
1/3.
So I can write this as timesing by 1/3. It's the same thing as dividing by 3. So is this a type of sequence? Yes. What type? Geometric. It's infinite. And if I wanted the 50th term, okay, if I wanted the 50th term, which one would I use? Explicit, and it would be A1 times the ratio to the n minus 1 power. So that would be 27 times my common ratio is 1/3 to the 49th power. And if I was to do this in a calculator, you would do this first, which means you take 1/3 and raise it to the 49th power first, then times by 27. And when you do that, if you wanted to try that on your own, you would have to put this answer in what we call scientific notation, and it would be 1.12 times 10 to the negative 22nd power. It would be a tiny, 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 tiny number. So like I said, look for a portal, look for those pages that you can finish up.